All right, hey folks, at this time we've learned some rules, shortcuts if you will, on computing derivatives. We have a lot of quick shortcut rules to help us in the process of differentiation. In section 3.3, we learn a special rule called the chain rule that makes all of those rules we've already learned just a little bit more powerful. So the objectives we'll look at in section 3.3 is objective 1. We're going to look at differentiating power functions using the chain rule. Objective 2, differentiate radical functions using the chain rule. And objective 3, differentiate rational functions using the chain rule. And then the fourth objective, we'll just look at an application where the chain rule is utilized. So to get started here, we just need to review from algebra that when you have a function of the form h of x equals f of g of x, that f of g of x, that was called a composition of functions. To differentiate any composition of functions, we're going to use what is called the chain rule. Now, to understand where the chain rule comes from, I'm going to utilize the following example. So in this example, we're going to consider the function f of u equals u cubed and g of x equals x squared plus 1. So this example is going to allow us to discover or see where the chain rule comes from. And then we're going to do three things here. And again, as always, make sure you write all this down because I'll head off to the chalkboard here in a moment. So in part A, we're going to do some, old algebra. We're going to compute the composition f of g of x. Then in part B, we're going to differentiate the result of part A. And then in part C, well, we got a lot of stuff going here. We'll compute f prime of u, g prime of x, f prime of g of x. That's like a composition, actually. And finally, f prime of g of x times g prime of x. So make sure you have all this written down. Pause the video if necessary, but write it down because I'm heading off to the chalkboard to work through this, and hopefully we can discover the chain rule. All right, folks, in this example, we're going to try to discover what this chain rule is all about. And so for this example, f of u is u cubed and g of x is x squared plus 1. So in part A, we're just going to do some old algebra. We're going to evaluate this composition of functions, f of g of x. So remember to do f of g of x, that would be f of, g of x, which is x squared plus 1. And then the f of x squared plus 1, we're going to take x squared plus 1 and toss it in here for the u. That's how you evaluate a function. So we get f of x squared plus 1 is x squared plus 1 quantity cubed. So that's f of g of x. Part B, it said differentiate the result of part A. So I just shortened that notation. I just shortened all that English down to we are going to differentiate with respect to x, f of g of x. So we have to ddx, or differentiate, the result of part A. Well, that was x squared plus 1 quantity cubed. Okay, now right now the only way we have of differentiating x squared plus 1 quantity cubed is to take x squared plus 1 and multiply it by itself 3 times. And if we do that, x squared plus 1 times x squared plus 1 times x squared plus 1 will give us x to the 6th plus a 3x to the 4th plus a 3x squared plus 1. Well, now we can get the derivative of this. We can do term-by-term differentiation. It's using the sum rule in conjunction with the power rule to get the derivative to be 6x to the 5th plus a 12x cubed plus a 6x. Okay, now I'm going to simplify this just a little bit. I can factor out a 6x. That gives a 6x times x to the fourth plus a 2x squared plus 1. And then one more step, x to the fourth plus 2x squared plus 1. That factors. That factors to x squared plus 1 times x squared plus 1. Or in the most condensed form possible, 6x times x squared plus 1, quantity squared. So keep in mind, this is the result of ddxing, differentiating x squared plus 1 cubed, which was really the derivative of, that was the composition, that was f of g of x. In fact, let me write that down. This was the result of when we ddxed, or we differentiated with respect to x, f of g of x. All right. Yeah, looks like there's a lot to do in part C, but it really isn't that much. First is compute f prime of u. So f prime of u is 3u squared. Let's get g prime of x. So here's g of x. So g prime of x is 2x. All right, now it's a composition of functions to do f prime of g of x. So f prime of g of x, well, that's f prime of g of x. G of x is x squared plus 1. So now to evaluate f prime of x squared plus 1, we take x squared plus 1 and we put it in here for the u. And that gives us 3 times x squared plus 1 quantity squared. So that's f prime of g of x. Then the final thing, it says take f prime of g of x, multiply it by g prime of x. So take f prime of g of x, multiply that by g prime of x. Well, we know f prime of g of x, it's right here. 3 times x squared plus 1 quantity squared times g prime of x, which is 2x, which gives us, if we multiply this together, 3 times 2x is 6x times x squared plus 1 quantity squared. So check it out, folks. When we did this multiplication, we got the exact same result as we did in part B. Part B was found when we differentiated f of g of x. This came about, we got this answer here, by doing f prime of g of x times g prime of x. So now, folks, since we got the same result in part B as we did in part C, 6x times x squared plus 1 quantity squared, it seems reasonable to say, since we got the same result, that means when we differentiate f of g of x, what's written in red, you can get the derivative of f of g of x by doing f prime of g of x times g prime of x. And in short, that's exactly what the chain rule is. So let's head on back to the slides, and I'm going to formalize exactly what the chain rule is. This example was kind of to give some meaning to the chain rule. But let's head back to the slides and formalize it. All right, folks, that example we just looked at really illustrated the mechanics and the power and what it is, the chain rule, what I'm talking about with the chain rule. So let me officially write down what the chain rule would look like. The chain rule says that if, y is a function of u and u is a a function of x, so u is g of x, and they're used to define h of x. H of x is the composition f of g of x. Then the derivative of the composition, h prime of x, equals f prime of g of x times g prime of x, provided, of course, those derivatives exist. And that's exactly what we just discovered in the previous example. Now we can specialize this a little bit to say if you have a function of the form, h of x equals some function raised to a power, the power is just a real number. You can use the result of the chain rule to create something called the generalized power rule, which says if u is a differentiable function of x and n is any real number, then if your function is the form u of x to the n power, then the derivative is n times u of x to the n minus 1 times u prime of x. I mean, that's just restating the chain rule. The key in doing the chain rule is what I call noticing the inside function and noticing the outside function. So I'm going to be talking about the inside function and the outside function in the following example. Again, write this in your notes. So in this example, we're going to determine derivatives for those two functions. And so we have two parts, an A and a B. So write it in your notes because I'm going to be heading off to the chalkboard to do this example, and then I'm going to have a few for you to practice. Okay, as I just mentioned with the chain rule, the thing about the chain rule is being able to identify the inside function and the outside function. And it's really not that difficult. So let's look at part A here. You're asked to differentiate f of x equals the quantity 7x squared plus 1 to the 6th power. So for this one, I think it's pretty clear that 7x squared plus 1 is the inside function. I mean, it's inside parentheses. It is the inside function. The outside function is raising to the 6th power. So to get this derivative using the chain rule, you start off as you would normally do. Bring the exponent out front. It's like the power rule. Bring the exponent out front and then subtract 1 from the exponent. So at this time, we've kind of done the derivative of the outside function. We've done that f prime of g of x. Now the chain rule says you have to multiply it by the derivative of the inside function. The inside function, think of that as the g of x. It's the inside function. So this is times the derivative of the inside function. Well, the derivative of 7x squared plus 1 is 14x. And if you want, you could take the 6 times the 14x, multiply that together to get an 84x quantity, 7x squared plus 1 to the 5th power. But that's it. That's all there is to it using the chain rule. So let's look at part B. G of x is 6 times the quantity 4x squared plus 1 to the 8th power. So here, the inside function is the 4x squared plus 1. The outside function is the exponent of 8. I mean, 6 is just a constant, so it's like a constant multiple here. So to get the derivative, using the chain rule, we do it like what we normally would. Let the 8 come out front, subtract 1 from the exponent. So that's like the f prime of g of x part. So we've done the derivative of the outside times the derivative of the inside function times the derivative of the inside function, which is 4x squared plus 1. So that's times an 8x. And if you want, you could do the 6 times 8 times 8x. If you wanted to simplify it down any more, you could do that. So that's all there is to the chain rule. Don't be deceived. It might look friendly, but this rule is very, very, very powerful. It makes all the other rules more powerful. This is going to be with you for the rest of this calculus course. Even in the second half of the course, when we start to undo our work, when we start to do things called integrals and we start to integrate, which is finding antiderivatives, you still need to remember this chain rule. So what I'd like you to do right now, I'm going to ask you to pause the video and do some exercises in section 3.3. I would like you to try 18, 20, 60, and 62. So there are 4 of them I want you to try right now. So pause the video, go to the section 3.3 exercises, do these 4. Once you've done them, I'll be here at the chalkboard and I'll work through the solutions and hopefully you'll have the correct answers. All right, in number 20, you were asked to differentiate, number 18, you were asked to differentiate the function quantity 2x cubed plus 4x plus 3 raised to the third power. So this is using the chain rule. So you should have as the derivative 3 times the quantity 2x cubed plus 4x plus 3 squared. That's the derivative of the outside function times, now the derivative of the inside function, 6x squared plus 4. And you must put that in parentheses. And that's all there is to it. So 20, you were asked to differentiate f of x equals the square root of 7x plus 6. Okay, here I think a little algebra is in order to get us started. In other words, to rewrite the square root as 7x plus 6 to the 1/2 power. Then the calculus is pretty straightforward. The derivative is 1/2 times the quantity 7x plus 6 to the negative 1/2. So that's the derivative of the outside times the derivative of the inside. Well, the derivative of 7x plus 6 is just 7. And that's it for number 20. So for 60, now bear with me as I do a little erasing here and get number 60 written up on the board. So for 60, you were asked to differentiate the function x squared times the square root of 2x squared minus 11. All right, I'm going to start off with a little bit of algebra first. I'm going to rewrite that square root as an exponent of 1/2. And now it's time to get the derivative. Now keep in mind here, you have another rule in play. You have the product rule. You have the function x squared, and it's multiplied by the function 2x squared minus 11 to the 1/2 power. So we have to remember the product rule. So you remember the product rule. The product rule says derivative of the first function times the second function plus the first function, and better give myself a little bit more space here, times, so we have the first function times, okay, now the derivative of the second function. And when we do the derivative of the second function, we have to remember the chain rule. So when we differentiate the second function here, we have 1/2 times 2x squared minus 11 to the negative 1/2. So that's the derivative of the outside, times the derivative of the inside function. Well, the derivative of the inside function is 4x. And if you want, there's a lot of simplifying you could do here. I'm happy with this as a derivative. I'm just going to go ahead and show a little bit of the simplification. just a little bit. We have x squared times 1/2 times 4x. Well, we know the 1/2 times the 4 is 2. X squared times x is x cubed. So that would give us a 2x cubed times 2x squared minus 11 to the negative 1/2. You know what? I have just a little bit of room. I'll show you a little bit more simplifying that could happen here. You could take out a common factor. You look at this term and this term. They both have a 2x in common, so we could factor out a 2x. Both of these terms also have a 2x squared minus 11 as a common factor. But it's 2x squared minus 11 to the negative 1/2 power that we would factor out. Remember, when you take out a GCF, you're always taking out the smallest exponent you see. Negative 1/2 is the smaller exponent. So if I factor a 2x squared minus 11 to the negative 1/2 power, if I factor that out of the first term, I'm just going to be left with a 2x squared minus 11 to the first power. Because if I were to distribute back in, these bases are the same. I would add the exponents, gives me a 1/2. If I factor quantity 2x squared minus 11 to the negative 1/2 out of this term, it looks like I'm just going to be left with an x squared. Well, since I've done all this work, I might as well finish it off. Might as well go one more step and finish it off. And that's to take care of stuff in the square brackets. Turn it into parentheses now. You can combine like terms. 2x squared plus x squared is a 3x squared. Okay, yeah, I could rewrite it without a negative exponent, but I'm done simplifying. So keep in mind, this is the derivative. Everything after this is just algebraic simplification. So hopefully you have the derivative, which was the result of using the product rule and then in conjunction with the chain rule when we differentiated that. So let's see, I asked you to do one more, number 62. So let me erase the board so I can get number 62 up here. So for 62, you were asked to differentiate the function x squared over 4x squared minus x plus 5, all that's to the third power. All right, now check this one out. Got to use an old rule, the quotient rule. So here we are using the quotient rule. So remember, in the quotient rule, it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And when I differentiate the denominator, I'm going to be using the chain rule. So when I differentiate the denominator, the 3 comes out front, subtract 1 from the exponent, times the derivative of the inside function. And the derivative of the inside function is 8x minus 1. Again, make sure you put that inside parentheses. And then all of that junk's over the denominator squared. So if I take a 4x squared minus x plus 5 to the third power, and then I square it, that'll make it the sixth power. Yeah, there's a lot of simplification I could do here. I'm not going to, I did on the last one, but I look at the numerator, and in the numerator I could take out a common factor of, it looks like a common factor would be x times quantity 4x squared minus x plus 5 squared. So I could factor that out, I could simplify. I'm stopping here. That's the derivative. All right, so in doing the chain rule, you noticed in these last two that I asked you to do, 60 and 62, the chain rule was one little piece of using the product rule in number 60 and the quotient rule in number 62. But let's head on back to the slides, and I believe when we head back to the slides, we're going to look at dealing with radical functions a little bit more. So let's head back to the slides and see what's up. All right, so hopefully that example made sense. You're getting a little more dialed in with how to use the chain rule, the power of the chain rule, noticing the inside function and the outside function. Also, hopefully when you did number 20 and number 60, you saw that being able to write a radical as a rational exponent was quite important. And in general, we can take the chain rule or the generalized power rule and apply it to radical functions, just like we did in number 20 and number 60. So if you have a function f of x equals the bth root of g of x to the a power, so b is the root index there, that can be rewritten as g of x raised to the a over b power. So I know back in algebra you saw how to rewrite radicals as rational exponents. That's just an important skill to have in calculus. It just makes the calculus doable. So let's look at another example. Here the function f of x is the fourth root of 7x to the fifth plus 20x minus 8, and we are going to determine the derivative. So write it down because I'm heading off to the chalkboard to do this one. All right, in this example, we're asked to differentiate the function f of x equals the fourth root of 7x to the fifth plus 20x minus 8. And so the first thing we should do, and we just saw on the slide, is to just rewrite this radical function, rewrite it with an exponent. It's called a rational exponent. So the fourth root, I'll rewrite that as the exponent of 1/4. So just, it's one little step of algebra, rewriting the radical with a rational exponent. Now we get the derivative. Well, it should be pretty straightforward. Going to use the chain rule. The 1/4 comes out front. That's the derivative of the outside function. Subtract 1 from the exponent, so that gives us a negative 3/4, times the derivative of the inside function. Derivative of the inside function is 35x to the fourth plus 20. And again, make sure that's in parentheses. And that's it. That's as far as I'm going to go on this one. So I'm going to give you one more to practice, because it's just practice rewriting a radical as a rational exponent and then getting the derivative. So I would like you, section 3.3 exercises, to do number 52. Pause the video, do number 52. Once you've done it, restart the video, and we'll see that you hopefully have the correct answer. In number 52, you're asked to differentiate the function f of x equals cube root of 4x minus 3. So, first thing we do, rewrite the radical. So cube root becomes 4x minus 3 to the 1/3 power. Then the derivative, using the chain rule, 1/3 times 4x minus 3 to the negative 2/3. It's the derivative of the outside, times the derivative of the inside function. So the derivative of 4x minus 3 is 4. That's it. So hopefully you got number 52. So let's head on back to the slides and see what else we can do with the chain rule. All right, so next up, we're gonna take a look at some rational functions. We can use the power rule, or generalized power rule, the chain rule, if you will. We can use that to help us differentiate certain rational functions. I would tend to say you might want to consider this rule especially when a rational function has a constant in the numerator. So when you have a constant in the numerator, it's a rational function, constant in the numerator. Rather than cranking it through the quotient rule, doing a little bit of algebra to rewrite the function can make the calculus a lot easier. So let's look at this example. Here the function is f of x equals 5 over the quantity 2x squared plus 7x cubed. We are going to determine the derivative. So please write this down. Going to head off to the chalkboard to do it, and I'm going to review an old rule of exponents from algebra that will help us rewrite this function and make the calculus much easier. All right, we just mentioned on the slides that sometimes when you have a rational function and the numerator is simply a constant, rewriting can make computing the derivative a little more friendly than going through the quotient rule. And we can do this by using, there's this old rule in algebra that says b to the negative n is 1 over b to the n, well, as long as b doesn't equal 0. So it's an old rule of algebra that tells you how to rewrite negative exponents. Negative exponent, you can rewrite it as 1 over b to the n. Well, likewise, if you have a 1 over b to the n, you can rewrite it with the negative exponent. Notice on this example, that's exactly what I'm going to do. I'm going to take the 2x squared plus 7x to the third power, which is in the denominator. I'm going to rewrite it with a negative exponent. So my first step here is algebra. It's taking the rational function that had a constant in the numerator and rewriting it with a negative exponent. Now look how friendly it is to get the derivative. To get the derivative, using the chain rule, we let the negative 3 come out here. 5 times negative 3 is negative 15. Subtract 1 from the exponent. So subtract 1 gives me a negative 4 times the derivative of the inside. Well, the derivative of the inside is 4x plus 7. And if I want, I can do one step of algebra to clean it up, and that's to get rid of that negative exponent now. So I'd have a negative 15 times 4x plus 7. So I get rid of the negative exponent by dropping it back down to the denominator. And that's all there is to it. So it's, I think, one step of algebra made the calculus very friendly. I could get the exact same result by not doing this initial algebra step and just cranking that function immediately through the quotient rule. But the quotient rule is just a little bit longer and it's a little bit more cumbersome. I just think this is easier and quicker. So let's head on back to the slides. It should be about time to do an application, but let's head back to the slides and see. All right, folks, the final thing we're going to look at in this section is an application where the chain rule is involved. So, as always, write this example down in your notes because I'm going to do it at the board. Here that function, 7.24, the fifth root of x minus 1. That represents percentage of people who has diabetes. X is the number of years since 2000, and f of x is the percentage. So at the board, I'm going to write down the function, and we are going to evaluate f of 10 and f prime of 10 and interpret each. So get this written down because I'm heading off to the chalkboard. All right, this was an application. I just wrote down the function, what we were asked to do. Quickly for this function, x was the number of years since 2000, and f of x was the percentage of people who has diabetes. So we're supposed to evaluate f of 10 and interpret, evaluate f prime of 10 and interpret. So, well, here, I'm going to go ahead and first get f prime, get the derivative. I will begin by rewriting the function. Instead of seeing the fifth root of x minus 1, I'm going to rewrite that as x minus 1 to the 1/5 power. So when I get the derivative is 7.24 times 1/5 quantity x minus 1 to the negative 4/5 times the derivative of the inside function. So the derivative of x minus 1 is 1. Okay, so I have the derivative. Now let's go about answering the questions. Evaluate f of 10. So let's see. F of 10. So here's my function. So I'm going to evaluate f of 10. So I put 10 in for the x, and I did this. And when I use my calculator, I put 10 in for x. I get 11.24. And I went ahead and I rounded that to the second decimal place. So let's interpret. What does this mean? Well, x was the number of years since 2000. So an x value of 10 would correspond with the year 2010. So in 2010, there were about this number, that was a percentage. So about 11.24% of the population or of people who had diabetes. Now we're supposed to evaluate and interpret f prime of 10. So let me come right here. F prime of 10. So here's my derivative. So I toss 10 in for the x, use my calculator, and I get f prime of 10 to be, again, I'm rounding it to the second decimal place, 0.25. So this means, okay, again, x was number of years since 2000, so 10 corresponds with 2010. So this means that in 2010, the percentage of people with diabetes was positive number, so increasing at a rate of 0.25% per year. And you could do the following. I'm not going to write this down. I'm just going to babble it. You could do like a super interpretation. You could just do one sentence where you interpret f of 10 and f prime of 10 in one sentence. And it would be something like this. In 2010, there were about 11.24% of the people who had diabetes, and that was increasing at a rate of about 0.25% per year. All right, so you know what? I'd like you to practice just one application using the chain rule before we go any further. So here in section 7.3, I'd like you to try number 74. So go ahead, pause the video, do number 74 here in section 3.3, and as always, once you finish it, restart the video and I'll be here at the board working through it. All right, folks, here in number 74 it says, during its first season, the number of viewers who watched the new television series It Ain't Me can be modeled by that function, the cube root of 50 plus 2x quantity squared. X is the number of weeks since the series has been airing, and f of x is the number of viewers in millions. Evaluate and interpret f prime of 13. So we have to get the derivative. And the first thing I would do is algebra. I would rewrite the radical function as 50 plus 2x to the 2/3. Excuse me. So to get the derivative, let the 2/3 come out front. That's the derivative of the outside function. Subtract 1, so we get a negative 1/3, times the derivative of the inside function, which is 2. Okay, now we're supposed to evaluate and interpret f prime of 13. So f prime of 13, so I put 13 in for the x, and when I do that, and I use my calculator obviously, I get 0.314775. I mean, that's enough digits to carry that out for. So what does this mean? What's the interpretation? Well, x was the number of weeks since the series has been airing. Let's start off by saying 13 weeks. Since the series has been airing. The number of viewers was, it's a positive number, so it was increasing at a rate of, okay, now here's where you have to make a decision. You either write this number down, remember that's in millions, so you'd write this number down, so you'd say 0.314775 million viewers per week, or you convert this to an actual number. Since it's in millions, you could, let's see, multiply by 10, 100, 1,000, 10,000, 100,000, million. So you can move the decimal point to the right and you would say 314,775 viewers per week. So it's either this number, million viewers per week, or it's 314,775 viewers per week. Both are correct. I don't care. So for this one, I think I'll just write it as 0.314775 million viewers per week. And seriously, folks, if you're looking at it and you're saying, gee, Bill, I would have said 314,775 viewers per week. That's awesome. That is correct. So that's it for section 3.3, the chain rule. So now you're ready. You can head off and do all the exercises that I assigned for section 3.3. Thanks for watching.